to convert your your x equation to solve for t. Just transform your equation. Solve for t, and then you're going to substitute in for the t in the y equation. This eliminates your parameter. It brings it back to x and y. Now, there's a number of ways to do this. Remember, you have to square this first, order of operations, and then you can reduce it. If at this point you leave this, this is fine with me. If you want to pull out the 1/2, this is actually your vertex form of your equation. It's a lot easier to put in your y equals, obviously, than your standard form, but it's a parabola with a vertex of 7, 2. It's opening up, and it has a little bit of a stretch to it. So we can find it, we can graph these guys, and get that sketch, and then find this one. You can put it either one. This is our standard form. I went with standard form because that's what we've been doing. But personally, I think the vertex form is easier because it gives you the y equals. And it might make a little bit more sense. You can still pull out your vertex from this one. And see that it's going to be a little bit of a stretch here. Just that we put the squared on the other side. Good? Can everybody do these? Solve for one, plug it into the other. Okay. If you do the parametric sketch first, you can see one of them is a squared. So the one you're plugging into, the one with the squared, is going to give you that sketch. That's going to be your parabola. And since it's going into the y, it's going into your t for that. You're putting your x in there to the y equals. You kind of already have it set up, y equals. This one was the opposite parabola. You're getting the square, putting it into the y. So now, the square part of this is going to be your y squared. If you do this, and you solve for t, this is a plus or minus. You have a couple of ways to do this. If you plug it into this, you can actually do this both ways. 6 times the negative of this, so I'm just going to make it the negative. If you left it like this, this is fine. And then 6 times the positive of this. I would prefer the rest of the equation to make it look like a parabola, but if you're going to put it in your y equals, this is easiest for your y equals. You'll see it's the same exact sketch. We get to this equation form by squaring this to get rid of your radical. And by squaring this, this is the piece that we get to for your standard form. If you're going to put it in your y equal, this will work better. Or you can take the square root of that mess, subtract the 3, and then put it in your y equal, whichever one you want to do. If you just recognize from here, here's your vertex. And -6, -3, you're kind of seeing the y equals, you're kind of finding your vertex. You pretty much know it falls there. I think the rest of them are a little bit easier. They kind of fall into your cosine squared plus sine squared equals 1. Just remember your degrees, your mode has to be in degrees to do this. Or radians, whichever one this one won't matter. But when you get here, you can see your formula coming through. You can see it's equal to 1. This starts your ellipse or your hyperbola. And when both of your denominators are the same, you have a circle. It's a special form of an ellipse. Your center is at 0, 0. It's going 3 away from the center. So that gives you a circle. If you left it as an ellipse, I'm fine with that. Are these a little easier to do? And then when we have a plus and minus, you can see that centers are offset. They kind of make a little bit more sense. But your t-step has to go from 0 to 360, or it's not going to make the complete ellipse or the complete hyperbola. And it's pretty cute how it makes the hyperbola. It does one piece, goes across the next, and then comes back and finishes it. You can use your Other form of your cosine squared plus sine squared equals 1. Use your tangent squared. Set up a hyperbola. You want it equal to 1, so you're going to subtract to the other side. That gives you your hyperbola. Okay. These are great questions. I can tell you one of them on the final looks real similar to these. Okay, this is where your center is offset because it's got something plus or minus in there. So you're going to solve for your cosine t, your sine t, that's where your parameter is. And you're going to use your cosine squared plus sine squared. Don't FOIL that out, leave that in there. This again was a circle, a special ellipse, the radius of 5. The center is a little offset. We're good with these? Alright. They pretty much all work the same. Whether it's 2t or t, that's still your parameter. So set this up. This was an ellipse. Why do we know this is an ellipse? It's a plus, and the minus is the hyperbola, and your two denominators are different. So it's not a circle, it's an ellipse. Your center is at the 0, 0. And the last one, you're a little off-centered. You have an ellipse. Which one is the major axis? The x or the y? The y. Good. In an ellipse, the larger denominator is the major axis. And we can kind of see when we graph it from the beginning that this is coming like this. Questions on any of these? We're good? We can eliminate the parameters? All right. So we're going to start. These are great for objects that make a parabolic path. And you've done this before. You've shot arrows, launched rockets, thrown balls. But you did this, and when you did it, whatever it is you were charting, usually we did time and we did height. Or we did vertical distance and height. You couldn't do all three. Now, with your parameters here, we can throw in one more. We can throw in time, and we're going to see time go on your calculator. It's pretty cool. We start off with basic equations. We have an x1. This is your horizontal component. And isn't x the horizontal axis? Right? Any changes in the horizontal axis will go in the x1. Y is your vertical axis. Any change in a vertical axis will go into your y1. So we've got an application. An arrow is shot with an initial velocity of 205 feet per second at an angle of 48 degrees. Find when, time, and where horizontal distance the arrow will strike the ground. Okay, and we're also going to see how high the arrow went, and we're going to add that to this. Now, you're going to start by doing this. You're just going to pull out your information. They give you the initial velocity. You got to just make sure that everything is in the same denomination. Like if it's feet, everything you do is in feet. If it's miles, everything you do is in miles. So sometimes they give you a wind speed in miles, they give you a velocity in feet, we convert it. T is important. Then we have the cosine of the angle. What was the angle of elevation? 48. Because we're using degrees, your mode has to say degrees. Okay. Now, the wind speed. This one doesn't have a wind speed. However, if you're a baseball player, you're up at bat. It's a strong wind. The wind is blowing right at you. When you hit the ball, what happens because of the wind? It slows it down. So the wind speed is working against you. So we're going to subtract your wind speed. If I'm up at bat and the wind is behind me, it's going to push my ball a little further, right? So we're going to add your wind speed effect to that. This one has no wind speed. It also has no vertical distance. He's not standing 3 feet off the ground. He's actually laying on the ground shooting his arrow. But that's because I didn't want to put a lot of different things in there. Normally when you shoot an arrow, probably your arm's length up, it's at least 3 or 4 feet by the time you shoot. But we're having him lay on the ground just so that we don't throw a lot of extra things in here. So we're going to do this and keep this simple first time around. This is our horizontal distance one. We're going to put your y in here. It starts off the same way. It's a sine. Y is always with sine, x is always with cosine. Same angle. Now, if he was 3 feet off the ground, 4 feet off the ground, it would be a vertical change. I'd put it right here, +3, +4. He's standing on a mountain, +20. But he's not. He's laying on the ground. This piece right here, you need this piece to make your arrow turn back. This is your gravitational pull. It's normally, I think, 32 feet per second. Am I right? 32 square feet per second? 32 feet per second. But something with the parabola, it makes it 16. So this is standard. It makes the arrow actually get pulled back to the ground. Otherwise, it would continue going straight up, and you'd never see it turn. So we've got something that's following this path. This is your horizontal distance. This is your vertical distance. And time is right here. Time is running with us. That's the difference when we use your parametrics. So we're going to put this in your calculator. Make sure your mode says degrees. Make sure you're in parametric mode. And you're going to hit your x equal. You're going to put both of these in. 205, don't forget t. Cosine 48. Then you're going to come down and put your y component in. Same velocity, don't forget the t. Sine 48. And only thing we did was the gravitational pull. -16 t squared. Now, before you hit graph, let's go to your window. Your t-step, this is your time. So an arrow to hit the ground probably does not take very long. So I estimated 10 seconds. So my time is going from 0 to 10. T-step 0.5. Your x max. How many feet away from you do you think your arrow would land? Don't use mine. So I'm not really sure. I'm going to put 500 in. I really don't know what it takes to hit an arrow. My x-min and my y-min have to be 0 because you have to be in quadrant 1. Now my y-max, again, I'm not really sure how high my arrow is going to go. I'm going to say 500 for that also. Just to show you what you're going to have to do. Now, when I graph this, I noticed that my height probably is okay, but what's off? My x-max. So I need to be able to see this guy come back down and hit the ground. So I go to my x-max. I generally double unless you feel like you're really far off. And I still am not that great at this. So I double it again. Am I ruining anything? No. I just need to be able to see it turn so I can trace this thing. If I don't see it hit the ground, I can't find out where it hits the ground. This we solely do on our calculators. There's no algebraic solution to this. So we can see he shot the arrow, it went straight up, it came down, followed a parabolic path. Now, my t-step is 0.5 right now. Watch what happens when you hit your trace. It's going to give you all 3 variables. Your time, your horizontal distance, your vertical distance. If I want to know when this hits the ground, I want to know what time it hits the ground. I want to know the x, how far away from me. And what will the y be? when the arrow hits the ground, what's the y value right here? 0. So I want this guy to be 0. I want my y to be 0. I'm going to trace my time till my y gets to be 0. Now, we generally go 3 decimal places. That's the hard part of this. But watch. We're going to trace. You see our time changing. There's 2 seconds. It's moving along from 7 seconds. I'm moving along. I'm 9 seconds. At 10 seconds, I'm still above the ground. I didn't hit yet. I'm sorry, at 9.5 seconds, I'm still above the ground, barely. At 10, I'm below the ground. At 10, I'm way below the ground. So I'm going to back it up 1. I know I have to be after 9.5. I want to hit my first negative value if I can't find 0. Because if I didn't hit 0, I didn't hit the ground yet. So if you went into your table right now, start your table at 9.5 and just do 0.5 right now, just so I can show you the difference. Here you are at 9.5, here you are at 10. So do you see where we hit the ground right in here? That's where it's hitting the ground. I need to get pretty exact in here. So I'm going to set my table starting at 9.5, and I'm going to go 0.001. I need 3 decimals. 3 decimal places. Guys, this is really important, so stay with me. Now I go to my table, and I'm going to watch my y till it gets the closest to 0. This isn't too far away, so it's not so bad. Right there. See it? At 9.521 seconds, it was still above the ground. At 9.522 seconds, I hit the ground. So my time is 9.522 seconds. My y value is as close to 0 as I can go. Bring this up here and go across to your x, because it's rounded in your table. My x value is 1306.150 feet. My arrow landed 1,306.15 feet away from me. But the tough part is we're going 3 decimal places. So we've got to play with your table a little bit. You don't want to set your table, you don't want to set your t-step that small, because it will take forever to get there. It will actually run that little thing like so small. Don't change your t-step. Only go in and change your table after you can approximate where it is. Now, I want to know how high this arrow went. I know it didn't ask for it, but I feel like knowing. How high did this arrow go? I have no idea how high arrows go in the air. So I'm looking for this one. And it's probably about half the time, don't you think? It's a parabola, so it's probably about half the time. So I could cheat and put my time in, or I can go back to my graph and I can say, okay, divide my time by 2, or trace again, and bring this to the closest to the top as possible. So somewhere on t equals 5. I like dividing the time in half, but if I divided this in half, I'd be about 4.7, 4.8, right? That's what I'm looking for. My y max down here. We're gonna have to play with this, but I got to get my time exactly. So if I divided this guy in half, if you divided this in half, it's going to be about 4.7. So here's an easy way to go. Go to your table, start it at 4.7, and see where it brings you. You want your y max to be increasing until you see the point where it starts to decrease. Now the hard part is it's rounding all the time. So I just want you to get in the ballpark. Watch this guy right here. Do you see it? Think of money. You were at 59 cents, you just went to 60 cents. You're still increasing, right? I'm 61 cents. I'm 62 cents. I'm still increasing. 63. Still increasing. I must have stopped increasing over here somewhere. Whoops. That was magic. I must have stopped increasing because it's been 64 for a very, very long time. And it's probably going down to 63. So some way, halfway between there, somewhere. So someplace about here, time, we'll call it this. And we'll call your Y value to be 3.264. I'm okay with that. We like 3 decimals, but if you can't, I don't really want you to have to be bothered to keep going like this and watching it down here. This is really annoying to watch it down here. You can watch it change down here, but if you give it to me this way, I'm actually fine. Don't set your T-step again, because your T-step takes a very long time. If I change my window and I make my T-step be 0.001, watch what happens. It's working. It's working. You're going 0.001 seconds at a time. It will take you a very, very, oh, I got a little part of my parabola. It's moving. It will go so slowly that it's so not worth it. So I gotta shut this off to get out of here somehow. Okay, that. So you do not want to set your T-step in your window. You want to leave this to be 0.5. If you can get a little closer, 0.25, 0.10, that's not so bad. Once you already have the graph, it's not so bad, but don't set it to 0.001. I was going to give you numbers 2 and 3. For homework. But if you want, we can do 2 together. Sounds good? All right. But you're going to have to help me. Okay. A golfer hits a ball with an initial velocity of 133 feet per second at an angle of 36 feet from the horizon, the horizontal. Find when and where the ball hits the ground. Secondly, will the ball clear a fence 9 feet high at a distance of 275 feet from the golfer? Right, so let's draw a little picture. Here's my golfer. He hits the ball. Now, when they hit the ball is right at the 0, isn't it? It's right down here. So this makes a little bit more sense. His ball is going to travel up, 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 come down, follow a parabolic path. We want to know this when it hits the ground. What is the time? And we want to know how far away. What was his final yards? What was his X value? Okay. Then, the second part of this is at some point a distance of 275 feet away. If there was a 9-foot high fence, did he clear it? A tree, fence, like statue, any kind of obstacle, did he clear it? So let's see if we can get your equations. What do you think the first one is? 33 T, good. Good. Okay. Do we have any other movement? Left or right, any wind speed? No. And your Y? Uh-huh. Good. Again, the minus 16t squared is what's bringing that parabola back down. That ball has to come back down. Minus 16t squared. The velocity, the gravitational pull is, correct me guys, it's like 32 feet per second or something like that, but
We're talking meters.
32 meters?
No, we're talking meters. It would be 9.8 meters.
9.8 meters. Okay.
I don't know what that is in feet.
What that is in feet.
It would be approximate.
Yeah. Yeah. So a meter's like a yardstick, right? So times 3, it would be, yeah, about that. 32. It's about the 32. Okay, so now, let's set your calculator up for this. Again, set it up. Let's change the angle here. Make sure you have your T in there. And it's got the minus. So let's see if we're close to that window. Because it didn't go as far as your golf ball went, right? That'd be a pretty long hit for your golf ball. It didn't go as far as your arrow. So let's see. Let's make them go 10 seconds again. And Y max, X max, how far does the ball usually hit? In feet. 600 feet? 300 yards, 600 feet?
Is your Y scale in one?
My Y scale doesn't really matter. It just makes that line darker. If you're going to have a high number, make your Y scale a little larger and it won't be so dark over there. And your Y max will probably make this be probably 100. It doesn't matter. No, you just need to see it turn. So we see him hit the ball comes back down, and it hits the ground. We want to know this guy right here, when it hits the ground. So we're going to trace.
Can you go back to your window?
Yeah. I figured it would take about 10 seconds. I figured my X-min went from 0 to 600. My Y-min went from 0 to 100, my Y went. I figured the ball didn't travel that far above the ground. Okay, and it can. Do you see your parabola turn?
See it goes down, and then there's like an extra line.
There's an extra line. Probably down here. You didn't change your velocities. You didn't change your equation. You're on the last equation still. You just changed the window. Okay, so now we're going to trace this guy, and we're going to see if we can come as close to the 0 as possible. And we're somewhere around 5, right? It's still below the ground here, but if we go up a little bit more, between 4.5 and 5. So I'm going to start my table. I'm going to start it at 4.8, just for the heck of it, and see if I can find where it hits the ground. I'm looking for my Y to be 0. You find you're too far off and you don't want to scroll, change your table set. Move you down a little further. If this doesn't bother you scrolling down, then keep it there. It's not that bad. This shows me how many of you are very comfortable with your calculators. So somewhere right there, about the 4.886 time, this is in seconds, 4.886 seconds he hits the ground. Okay, and how far away is this from us? Follow the one you're charting and just come over here. And X1 is 525,730 feet. Pretty good shot, I'm assuming, right? Now, we also wanted to know if it cleared a fence at a distance of 275. So what is it I'm looking for to be 275? My X or my Y? My X. at a distance of 275 feet away from me, that's my X. I want to know, was the Y, is he bigger than 9? Is he over me, over the fence? So my X, I'm pretty far off. So I'm just going to estimate this and say, what about 2.88? Am I close to that? I want a distance of 275. I'm pretty close. Maybe I want to go down a little bit more. I mean, I could do it with my trace button. We can do it here. We can bring your trace back. We can look for this guy to get close to 270. Whoops, close to 275. Oops, I didn't trace. We can look for this to be close to 275. Right about here, right past the 2.5. Sometimes you see it right on there. What did I say, 2.5? Okay, so I want this to be 275. So here's 275. So somewhere, and this is what you're going to have to give me. You're going to have to say, here's my time. Here's my X distance. I'm 275 feet away. And my Y distance is 95.283. So my ball is 95 feet high. Did I clear a 9-foot fence? Yes. I cleared the 9-foot fence. It takes a little practice, guys. What I want you to do tonight is to go over